Just want to tell a little quick story about the next presentation on LTE and security. We had a colleague that actually told these guys that you got to submit, and you submitted at 11:59 on the final day of CFP, and boy, yeah, with a minute to spare, the nick of time. I can't make this up. I mean, I just literally cannot make this up. And it turned out to be a very good one. So without much ado, Noble Trout and Chris Moore.
Thank you. Hi, guys.
Hello.
Hello. Thank you for coming out here, not sleeping in. We don't have an introduction slide, so I guess we'll introduce ourselves.
Yeah, you first.
I'm Chuck. This is Chris.
Hello.
We both work at a company called Ixia. Ixia does a lot of network testing. We test things all the time. How fast, how many, how secure, all that stuff. And both him and me had the opportunity to go into carriers and try out testing some very weird esoteric stuff that is acronym soup with no training or background whatsoever, and have to figure it all out and then test it for performance and security. And we had a lot of fun. So what you're gonna pretty much find out here is what this stuff is, how to find it, the protocol stacks, and
How to break it. Maybe?
how to break it, yes.
So not only carriers, like we had tier 1, tier 3, but we also had vendors. The network vendors came to us also. Oh, there we go. And pretty much neither of us have training in this, so we had to teach ourselves. And this is effectively what I would have wanted before we went into first carrier.
Yes,
So-
it would have helped me a lot.
Yeah. But instead, we just asked a lot of questions to the engineers that we work with, and they thought we were stupid, but we were curious, so they just went with it, I guess.
Yep, so let's start.
Yep. So I know there have been a lot of LTE talks here. We went to a great one yesterday. However, this one is kind of a preliminary, like 101 for LTE. This kind of gives you a background. I'm going to be going over like the 30,000-foot view of LTE. More specifically, mostly the EPC components, which is kind of the network backhaul. It has nothing to do with the EU-TRAN, which is the wireless portion. So
Everything here is Ethernet interface.
yeah, pretty much all those networking elements. So, and he's going to be going over like the 5 or 10 foot of the elements. So that's effectively what we're going over. Out of scope, pretty much everything else. There's so much depth to all of this that we just can't get into. So IPSec, we're not going to be going into that. The stingrays, MC catchers, baseband CPU compromisers, cool stuff that's in the news right now. Yeah, we're not going to touch because we haven't touched that.
Yeah,
So-
basically, we're going to help you. If you can get into the baseband of a phone, now we're going to tell you about all the fun stuff you're connected to.
Yeah. Okay. So everyone knows how the internet effectively works. This is how your grandmother sees the internet. She knows she has that brown or that blue box, Linksys box. Her laptop connects to it, and then she sees pictures of her grandparents or grandkids. So, yet I'm sure a lot of you actually know all the underlying protocols that can detail all of the messages, requests going through to look and to post those.
There's
those
a
pictures.
firewall in there. There's BGP routers, ASNs, and
Yeah,
packet routing and all
switches.
that stuff. And everyone pretty much here knows all that stuff.
Yep.
Right?
Okay, taking that, well, this is how your grandmother sees connection with a phone to get to Facebook. Well, guess what? You're pretty much not better than your grandmother at that point, because I'm sure most people are like her, don't know all of the underlying protocols to get to Facebook through a phone.
We're guessing most of you guys feel like it's all jazz handy until you get to the internet with your phone.
Yeah. So we'll kind of break it down. I think everyone knows effectively most of this. It's just a typical small, medium business network. You have your connecting stuff at the bottom, go through access points, get to edge switches, distribution switches, core router, some securities in there. Then you get to the internet and you're able to look at your pictures. Well, you know that, but here's the modern equivalent in the LTE world. It's crazy. Like, It looks like messed up spaghetti. If you actually look, this is an eye chart, but there are 3 different legends there. There are so many acronyms. There are actually acronyms that include acronyms. That's just how complex it actually gets.
And the internet is this tiny little place right
It's a
here.
small dot in that whole
This
mix.
little gray cloud. The rest is gobbledygook.
Yeah. In LTE's defense, not all of that is 4G LTE components. A lot of that is kind of last gen, previous gens, then gateways to talk to last gen technologies. But that's what we're dealing with.
So let's simplify it down a little bit.
Yeah, boil it down to like the base components of the modern 4G network. Here it is. You have your cell phones on the left-hand side, talking to the cell phone towers, and then you have like 5 or 6 other components talking to PDN, which is packet data network, which in this case, most cases, is the internet.
Yes, the telephone companies decided to come up with a new acronym for internet. They call it PDN.
In their defense, there could be other PDNs, corporate networks.
Like another internet.
Yeah, internet too. Okay, so you don't know this yet, so we're going to give you something. Decoder Ring from one of my favorite movies, Christmas Story. So with that, you'll be able to translate stuff on the left-hand side, the LTE equipment, to the analog in the IP world. Okay. No. So you have your UE, which is user equipment, which is speak for cell phone. That is laptop or tablet, whatever. Your entry point onto data network. Then that talks to your eNode B, which stands for Evolved Node B, which
You know what that stands for?
not really. I'm kind of faking it here, but let's go with it. Back me up.
All right.
No, Node B I think was the 3G nomenclature for a cell phone tower.
There is no eNode A.
No, there isn't. So that's equivalent to your wireless AP. Next, for your authentication, instead of being a corporate network, registering with AD and getting on there, you have your MME talking to database, which is the HSS. And then finally, you have user plane, which is SGW, which is equivalent to your edge router. Then that talks to the PGW, which is the same thing as your core router. Then you go out to your PDN. Now to pop all of that actually into the flow of a call, your cell phone connects to one of many eNode Bs, and then messaging takes place to the MME, which then registers you and then allows you to have a user channel, which allows you voice, video, data to the SGW, then pops you over to the PGW, and then to the PDN. And you can see funny cat pictures at that point. So that is a very, 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 very simplified call flow. Just the registration steps required to connect the eNode B unto itself can take up almost a whole session unto themselves. So, unto itself. Okay, so those are kind of the main 5 components that we're going to go over today. So the state of LTE, how it is today. There have been lots of releases of generations. So a generation actually means effectively equipment that is not backwards compatible. So 4G, if you're talking 4G, you cannot talk to 3G equipment unless there's a gateway between the two. So all of the standards, all of the releases have been done by 3GPP, which, you're like, they came out with the 3G standard, right? 10 years ago or so, 15 years ago. Why are they still releasing for 4G, 5G? They're just lazy and haven't renamed their organization. It's a regionally based thing with 7 regions. 2 out of Japan, 1 out of all of Europe, 1 in the US, 1 in China, then 1 in India. So.
And they keep changing the spec on us. So every time we try to reconnect and test it again, we have to go back and develop more code and fix things to make things talk to each other.
Yeah. And so we're at 4G right now, LTE. 5G is LTE Advanced. That's effectively getting rolled out right now by a few carriers in the US. It's not like a huge jump or change from LTE to LTE Advanced. It's same devices, different spectrum, just increases peak download speeds and network capacity from 10, 20 megs down to 300 megs down. So you'll see that, but it's not a huge difference with the EPC components that we're going to be going over today. This is killer. I hate this. So there are effectively only 4 large vendors in this whole space. So every single packet that you have running over LTE goes through these guys, and these guys alone. There are some startups that have played in this and still do play. A few of them have gotten gobbled up for better or worse. Some bigger players have been there, then just flamed out for different reasons.
Huawei might be in there too. I mean, but you're really talking like a handful at most of people that are involved in this.
So the implications are that, I mean, if there isn't much competition, there's not much reason to, I mean, make a better product, right? So they're not going to push themselves to develop
a more secure infrastructure. Yeah.
So another reason this is really insecure, interfaces. So interface is kind of service providers speak for a specific stack between 2 network components. Pretty much like S6A interface between me and HSS, that's
Diameter over SCTP.
yeah, SCTP, yep.
But like each of these is different and unique, like a special little snowflake.
Yep. So this is actually referring to 3G, but I mean, the same thing applies to LTE network elements. I mean, it's kind of obvious that there are vulnerabilities, they're known, and service providers know it. So they're not without issues.
And these are some of the interesting quotes that we've heard people tell us, or
Equivalent of. Yeah.
equivalent of. The most eye-popping one at the bottom, it comes straight from Arbor. And they said, the economics of consumer subscriber networks do not incent providers to implement security until a problem occurs. They're actual components on there by class, by
So it could be any
device.
of them, honestly.
Yeah. That would all be all grouped together.
Yeah.
But basically, that is corporate speak for you guys don't pay enough for your phones for them to worry about your security,
Yeah.
right? The other things that I hear from techs and people involved in this industry are, but it's hidden, or it's protected, or it's managed, or why would anyone ever do that, which we all hear all the time. And it's like, because.
So add all that together, lots of interfaces, barely any competition, known vulnerabilities, and you just have a glued together network that's like made of clay. It's not solid. Like a few years back, I remember Tier 1, a single element went down in Florida somewhere that brought down the whole East Coast for half a day.
Yeah, most of these things are like big giant refrigerator sized things, and they're like in a handful of places, the things we're talking about here. Is it my turn? Yes. Okay. So Chris talked earlier about mapping these things to things that you already know. So just to look it over again, to remind yourself one more time, that's where they go. Let's look at the first one, the MME. So the MME sits up over there in the corner, and it's the first point of interaction between your phone getting onto a network and getting authorized. So it's basically a gateway message management system between the database and the phone, so you can sort of manage your database any which way you want, in a way, or that's the idea. And it basically looks at your phone's IME ID and says, yes, you're allowed on network, or no, you're not, or here's your billing structure, or whatever, right?
Yeah, that's just control plane. It's not like voice and video go through.
No,
me.
this is just, I want to connect to the network. And they're pretty much unicorns. You're not going to find one at dumpster diving. Good luck. And they're really hiding behind some pretty big, physically secure areas. If you're like a tier 3 carrier, you can get away with 2 of them, right? So if you're probably Verizon, my estimates would put it at maybe 24 of them around North America. So there's not a lot of them, and if you take them down, then you have problems, because no one can get on the network. The MME interface is called S1 MME. And if you want to ask us what MME stands for, we keep remembering and then forgetting. Thank you. So it acts as a responder and initiator. It's a responder on the bringing up the phone conversation. It uses a stack called S1AP over SCTP. And It's used for control plane communication between the node me and the MME. General methods of attack that you can do to it. If you can use a compromised E node B, you now have a channel of communication to this thing, which then will allow you to go on into further places. Also, it does listen on SCTP port 36,412. So a future project we're thinking of doing is setting up a scanner for that port across the internet and seeing what's out there. There's no safety mechanism in place for DDoS mitigation on the MME itself. You can just flood it with attach requests and deny service to other people. So if you can figure out ways to make a phone just keep sending these attach messages, it won't be able to service other requests. There's also really no cryptographic authentication that we could find for the tower to identify itself to the MME. What that means is that what we saw for the most part was just a string of text from S1AP messages and then a list of towers that were known. So if you can guess the string, probably go with like tower 1, tower 2, or something like that, then you can probably talk to it.
And it usually has the provider's name in the string.
Yeah. The MME interface stack looks like this. There's a lot of attack surface in S1AP. It's a nested protocol TLV style thing, and I'll show you a screenshot of a packet dump of it. I suggest you fuzz it. It sends funny things and it messes it up. Sending valid state messages or confusing messages all brought it down. And then the SCTP stack was equally fragile. Fuzzing that just made it dump out, and I'll show one of those that I had. And messing around with stream IDs or other elements in it messes it up. Fragmented packets as well on these things is a nightmare. A bit of a digression on SCTP. It was developed for SIGTRAN SS7, which that's all I know about it. But what I do know is if you talk to old wizened bearded telco guys, they'll tell you that next year SCTP will replace TCP. And they keep telling me that, and I keep telling them it's not happening. It's meant to be a TCP replacement. It has a stream-based idea. So imagine if you could multiplex multiple TCP streams inside of a TCP stream. The only real advantage I can think of that is that if you start messing around with windowing and stuff, you can become less sensitive to packet loss issues and ramp up with opening the socket.
So we actually worked with our developer in-house when he was making our SCTP stack, and we weren't doing it very well. Evidently, the real SCTP stack that we were running against wasn't that good either, because we kept breaking it down because we didn't know what we were doing.
Yes, going back to not knowing what we were doing and learning on the way. So running a quick fuzzer against the SCTP stack on Ubuntu gave me this wacky-looking error message on dmessage. And then I wasn't able to rebind to the socket for 5 minutes. You can imagine that if you're using a Linux-based product to do your control plane messaging, this might potentially be an issue for you. And when you take an error and you put it in Google and get 0 results, you found something. Also, Chris found this one on Reddit when Heartbleed came out. SCTP stack had a lot of development work done it by Robin Siegelman, who was unfortunately the much maligned individual that introduced the Heartbleed bug. The Heartbeat package messaging system was directly taken from his work that he also did on SCTP, on SCTP. So we haven't had a chance to really dig into that, but I really have to think that I don't think many people have gone, I should probably go fix that over there. So that means you could leech off subscriber identities and other things off the MME if you logically follow the rest of that, right? SCTP points of interest. Are you guys keeping up with us? Is this like a good? Yeah? Okay. Hang on a second, I need to go.
But if there was a patch for SCTP, I'm sure the telcos pushed it because they're really good at patching.
So points of interest, when you start looking at the packets for SCTP, you'll notice that you've got source ports, destination ports. It is packet loss sensitive, so it acts a lot like TCP. But the handshake, I think, is it 5 packets or 6 to bring up each handshake. So there's a lot of handshake messages that go on. And then you have, you of course have TLVs in there. You have identifier numbers. They always seem to start at 0 when you open up a new SCTP socket. There's other things going on around there. And it's a pretty packed protocol, but not nearly as packed as S1AP. So you can sort of see all the, actually this is a great one, because over on the left-hand side, you see I've highlighted eNode B, and that's -1. That's the name of the eNode B. So it's in the clear text on the wire for identifying itself to the MME, okay? You can also see that these things are highly nested and rolled up, and typical history tells me that when things are rolled up like this, I've got a chance to really mess with TLV values and parsing issues along the way. Or there's a lot of edge cases you can test there, right? Also, if you're looking at S1AP capture and you're trying to sort of figure out how does this map to the stuff that's printed out on my phone when I go under About, right? So you see the MEID and IMEI, those are sort of like MAC addresses. They're unique identifiers for your phone. So you can easily identify those numbers in these control plane messages. And you can also identify the network that you're on, which is normally referred to as the APN. So if you wanted to write a scanner for looking for MMEs, you'd probably want to start off by grabbing an IMEID off a phone in the Verizon store and putting that in here, and then using that messaging, or Sprint or whatever if you were looking for them. HSS. So this is the database behind the monster, that's the MME. It uses the S6A interface for communication. The HSS is basically a narwhal that's behind the unicorn. You're really not going to see this one either. But it does exist. We've seen them in labs. It also uses SCTP. It's got its own special port there. And then it uses diameter over SCTP. So really, I don't understand the design philosophy here of using SCTP for this when you had TCP available to do this. Maybe someone can come back later and tell me why. But
They pin up the connection.
put your hand up. Multi-homing. Okay. Thank you, Phil. All right.
And usually between the ME and the HSS, there's a load balancer called DRA.
Yes, so the DRA will load balance these connections across multiple HSSs. So that's another device that you can choose to try to get into an attack. All right. Next device is your SGW. This is finally when you start getting onto the internet. So all the other messaging so far has been just to make sure that you have paid your bills and are allowed to be on the network, right? The SGW has two interfaces. One is control plane and one is data plane. S11 is data control plane. And it's used for the MME to tell it, hey, a phone's coming online and it's allowed to go onto the internet. So the phone never actually directly communicates with the SGW. It has the MME act as sort of a broker. So think of it really like an Active Directory server, right? You have a central point of authentication that then instructs and allows other things to happen. GDPC is actually a sane protocol. You can look at it and understand it, and it's pretty straightforward. It still is TLV's soup for the control plane version of it, and it runs over UDP port 2123. It allows you to bring up the context. So after you've done all of this packet loss sensitive stuff to make sure that you're allowed on the network, the last step to actually make sure that you actually have a connection to the internet is done with a lossy protocol. Once again, you're going to see this over and over again. I'll just say it one more time now. If you fuzz these things, they crash. That's all you have to do. And when you reboot this thing, it takes 10 to 15 minutes to come back online. The S1U interface. This acts as not so much as a responder or initiator. It's basically a tunneling service. So the tunnel packets either come from the tower to the SGW or they go back out. This is where you actually have your Garfy cat pictures and your Facebooking and all that stuff going on. a second. So if you start looking at the GTPU, which is different than GTPC, GTPU, which I think stands for GGSN tunneling protocols or something, right? Acronym and acronym. Yeah, GPRS tunneling protocol. And then GPRS is, yeah. Anyway, this one has a tiny header and then the IP packets and the TCP packets and the HTTP packets. So think of it just like you would think of VPN connections, right? This is the easiest entry point for you as an attacker because you're already controlling the stuff in the red area for the most part, right? Without having to get into the baseband of your phone, you already have an IP address, you can make sockets, you can make HTTP requests. The SGW also will do deep packet inspection and proxying of content to speed up delivery of stuff. So you can attack application layer stuff on proxies and things and see what happens. So yeah. And if you break into this thing, then you're looking at everyone's data traffic. LTE also introduced the feature known as bearer channels. Bearer channels allow you to put user plane traffic over different channels. Think of them like VLANs, priority, right? So basically you see T-Mobile offering like, watch all the Hulu you want, doesn't count against your data package. That probably goes over a different bearer channel than the rest of your application traffic, okay? The UE gets to decide which bearer channel to send for each type of traffic. And this does roll up in some way into the normal little Linux computer, or I don't know what the iPhone runs, that everyone roots all the time. So one way of trying to attempt to conduct toll fraud would be to put other traffic across the wrong bearer channel. You guys probably heard of VoLTE, voice over LTE. That's basically SIP phone calls over a LTE network. So one other thing that we did was running regular packet data traffic across that VoLTE network. And then, of course, everyone knows how to get free data by tunneling port number 53 for your VPN because they don't want to mess with DNS because it just breaks everything, right? All right, am I still good for pace and everything? You're good? Okay. PGW. So the PGW, this is where a lot of insanity once again gets introduced to this. So instead of having the SGW go, great, okay, now off to the internet, it goes, no, I want to put you through another thing. So it actually will take the IP packets off that GTP header and create a new GTP context between it and the PGW, okay? And that's called the S5 interface. So it's, if you can follow along at home, the MME has created a context and used GDP to create a context for you, and then the data traffic goes into the SGW, and then an entire different set of control plane, user plane negotiation occurs between it and this other device. This one also has another interface that connects to something called a PCRF that allow you to do a lot of billing and control and data analysis, but we don't worry about that today. This is basically your core router. So a lot like MMEs being very few and far between, you probably only find a PGW 1 or 2 in a city, right? The SGWs even, yeah, less than that, could be regionally based. And sometimes you actually see the PGW and the SGW rolled into one device for smaller carriers that don't need to worry about the complexity. So since it uses GTPC and GTPU, just use the same set of attacks that we were using against the SGW, and you'll be good. So let's talk about some of the security elements that are there. Most of them are worried about the carriers themselves and not so much you or network service reliability. So you do have DDoS mitigation, but it's to stop a DDoS attack originating from the phone network, not so much going into the phone network or anything like that. You see security gateways like firewalls to do VPN or to support roaming between different carriers. But that's for the most part what we've seen. Most of the questions we've gotten around that are, can you run SCTP traffic to test my firewall? And the answer is yes. And then the firewall's performance goes because it doesn't know what SCTP is and they haven't tested it or anything because no one's asked for it. So with your firewall insertion points will be in these sort of places right here. A lot of you probably discovered when you connect to the internet, it's one big giant SNAT network for a lot of them, right? It's a 10/8 or something. And the thing that does the source natting will sit right beyond that PGW, and it'll probably be a big giant refrigerator-sized firewall doing carrier-based NAT. Right. So I think, how many more slides we got? One more? That's it. So here is a documented list of all the things that we've crashed with some details of how we crashed them. We're not, naming any specific vendors or anything, but all of this sort of works against all of them. So yeah, it's sort of like 1998, 1999 all over again. I mean, you've just got like buffer overflows and stacks and things and parsing engine problems and screw-ups and yeah, that's about it. Anything for you?
No, that's pretty much it.
All right.
Questions?
We like Star Wars. Any questions?
So, what did you observe when you ran, data traffic into the IMS APN, into the bearer, IMS bearer?
What we were able to do is, okay. The question was, what happened when we ran data traffic across the IMS APN? A couple things. One is that since I can specify a different bearer channel and put the wrong data there, I expected it to reject that, to say, like the Volti instance, I expected it to say, this is not SIP, no. But instead, it just let it go through and routed it out. Yes?
So would you say that these vulnerabilities make SMS a lot less secure than they already are?
Do these vulnerabilities make SMS less secure than they already are? So that actually is a very interesting question because none of this has anything to do with SMS text messaging. That's a totally different beast. I know nothing about it. So like all your phone calls don't go through this, not until voice over LTE does. All of your text messaging is a totally different infrastructure. So like that big complicated network we showed had nothing to do with SMS. Yes?
So is the SGW where the carriers do HTTP header injection? And are they using one of those big four providers' tools to do that or something else?
So the question was, where are they putting that stupid crap in my HTTP header?
Good question.
We have a colleague who could actually answer that, and he's not here. My guess would be in the SGW.
Or right outside of it.
Or right outside of it. Like, there are proxying functions, so if they're doing proxying there, I'd expect them to also do that. All right.
That's it.
Thank you, guys.